Okay, so in this lecture, we're going to talk about something called kernelized regression. So this is I'm still part of the lecture theory of the regressions, but we want to talk about something slightly different here. So, for example, and this actually happens, and we are going to repeat these things in the classification as well. So you can see right here, and I mean, in terms of the and regression is basically we're trying to and find a line and to fit the to fit equations. But it's kind of like if you think anything in terms of we're trying to distinguish the blue dots and the red dots, that's like typical classification problems. This also happens as well. And you can see in this picture, just simple 2D data, we have like blue dots right here and the red dots in the middle. So it's very, obvious if we draw a circle right here, it can perfectly separate this blue dot and the red dots. However, that's like nonlinear function to separate this. So that's not usually not easy to come up with if we live in high dimensional things. But if we translate the coordinate system from Cartesian into polar coordinate to translate, this into like radius versus argument theta, then everything is being separated out very well. So you can see the red points is in the left and the blue points is on the right, and they will be a perfect critical radius right here, and everything above this critical radius will be classified as a blue. Everything below this critical radius will be classified as a red. So this is something that and give you some idea that if we actually transform our coordinate and rather than look at this Cartesian coordinate, sometimes it can make things a lot easier. In fact, that happens a lot in the last homework and the last questions. It's usually if we want to work with pixel values of images, it is a really bad and basis. It will be much better if we can just to work on the some transformations of the pixel values. So that could be so much meaningful than cell. Similar things. This is the similar and idea and similar data. But it's another way that we can do transformation is we can lift up this 2D and the data into much higher dimension. For example, this will be an x1 square, x2 square, then square root of 2, x1, x2. Then actually we can see these red points and the blue points, they living on this manifold. With that, you can see there's a possibility that we can create and come up with a plane in this 3D dimension perfectly separate blue points and red points. All right, so you can see right here. So this will be the red points, this and right here will be blue points. So this gives you some idea if you have a bunch of data right here, and it may not be easily for some regression problems. Maybe you can think about it. We can and come up with a bunch of new nonlinear features. With these new nonlinear features, it is possible, and we can fit things better, right? So this could be a good point. In fact, we did something like that before, which is in the polynomial regressions. Basically, while taking some polynomial so basis x to the 1, x to the 2, x to the 3, and so on, and x to the d as my basis, as my coordinate transformations, to higher dimensions. So we can do the regressions for the polynomials. But issue is this might not be, this might not be the only one. A lot of cases, polynomial could be a really bad choices. So we want to study something that is slightly different perspective. I think we kind of ignore that part previously. Previously, we assume the number of points is always bigger than the number of features. So that means n is always bigger than d. If in this cases we're trying to lift up and create more features and create more like random features and lift up into much higher dimensions, it is possible the number of features is actually bigger than the number of points. That means the d is n bigger than n. Sometimes it could be d is significant, even like much bigger than n. So how can we handle these kind of situations? Okay, so let me just go back to my notepad. Right here. So today we're going to talk about kernelized regression. So so the issue is, we need to come up with more more nonlinear features. In this cases, my input could be also in high dimension as well. So this could be quite significant. So and I just demonstrate that if we lift up into higher dimensions, it might be easier to classify all and to make the regressions to that. But usually, it'll be hard to know which kind of feature map or lift up will work for given data. So the way we do is we usually create a really high dimensional features. We create a significant higher features and hope our algorithm will automatically pick the right set of features by using lasso or whatever ridge regressions that we are trying to use right here. So that means, it's very likely we're going to create a lot of unnecessary features that to make whole and dimensional features is really high right here. So the key here is as I have feature mapping. In this case, I'm going to call it phi. This phi is from RD to RP. Okay, so that means I'm going to map our original data in RD into a much higher or rich dimensional feature spaces in RP. So in this case, my P is significantly bigger than D. So and of course, if D is equal to 1, which we have a talk about that, we can use the polynomial basis. Which phi is phi 1 of x. It's 1D, we don't need to put the vector sign here. Phi 2 of x and the phi k of x, which will be x squared to x to the k. Right, so this is basically polynomial and a polynomial basis. And of course, if it is d equal and d is bigger than 1, so and this is the cases that we usually encounter all the time in practice. And my feature itself is multidimensional. I think in the I mean, in the past and also in the homework, you already did similar things. Is what we do is we generate a bunch of vectors. So these vectors is called uj, j from 1 to p. So you create a bunch of and vectors. So this could be random vectors. I mean, it could be like Gaussian and random vectors. So this is actually, and it's in R and the small d. So each vector is in small d. So we can find out these features as follows. That is phi j of x is equal to cosine of uj transpose of x. Or, I mean, there are like multiple choices that you can do. You can do uj inner product of x squared and 1 over 1 plus exponential of uj transpose of x. So this is actually a scalar right here, u and x. So and you take inner product between u and x. So that gives you a scalar. Then and then after that you take the square of and out of that. So this becomes a and a scalar values. And of course, I mean, this j is coming and choose the j from 1 to the p. Then you have a bunch of like more features and to be created. So with that, and you can see this feature spaces can grow at a very large very quickly. And because you can arbitrarily create this and that kind of like and the random vectors you want very quickly. So in fact, that's one of the approach that we did in the homeworks. All right, so and you can see this is getting I mean heads up. So if we are working with a situation that and that's very common that my d is smaller by n. If we're just doing the linear regression directly on our small d, that's fine because we think about n is and it's still bigger than d. We can just using the normal regression approaches that we have. But now we are not working on the r small d. We are actually working on r p right here. In general, we assume this p could be significantly bigger than n. So this is assume. So that means if we want to write out this phi j x and j is from 1 sorry, I think that was not right. So we need to write up for all these features for this phi 1 of x 1 and I phi 2 of x of I phi phi p of x of I. This is actually has p and has p component, but that's just for and I of that, and I can be from 1 to the n. So you can see we really need a really large memory to store these features. And if we actually run this linear regression directly for this phi, it would take really, really long time. So the question is, if we have that kind of situation, can we come up with and efficient algorithms. So what does that mean is I want to avoid to calculate phi I phi j x of I explicitly. So that means I don't want to actually write down this whole thing or do any kind of specific calculation for this phi j x I. I'm explicit. Every time I want to write things out like this, it will be memory intense and computationally expensive. So how to approach this? This actually need to use some fundamental tricks in machine learning. It's called kernel. So you probably heard about this, but just in case you didn't, so this is a very basic definitions about the kernels. We're going to spend quite a bit time later on in the classifications to talk about the kernel tricks. So this is something you will see this again, again, again. I mean, this is probably the first time you see it, or maybe you have seen that in other courses. But this is something this is very extremely important. So this is very fundamental tricks in machine learning. So the definition is follows. So basically a function k is r from rd to times rd to r is called a kernel for a map, and which is a feature map phi if k x prime is equal to phi x dot phi x prime for all x and x prime. So if we think about this k evaluate for all x1 to xn. So if we evaluate at x1, x2 to x of n, so basically this we are getting is k, I'm going to call kij, is defined as k evaluate of xi and xj. So that, this like k automatically give you an n by n matrix. Right, so this is very important. And the n by n matrix, to calculate this n by n matrix, it only takes about n squared. If we can find a way to efficiently calculate each entry of this k, then we only need to operate with n squares. Instead of we work with the phi's directly, provided we can calculate these kernels efficiently. Okay, so the main idea, so this gives you the main idea right here. Is we actually want to represent our training algorithm. And the prediction rules. So because in regressions, they always have a two part. One is training, one is predictions. As a functions of k, x, and x prime. Right, so we're just trying to use this k function right here. Of course, I haven't, tell you how to calculate this k right here, and this is just by definition right here. So with this, if we can calculate this k kernel function efficiently, then we can avoid computing or storing very high dimensional features of phi xi. Okay, so this is very expensive to compute and to store the high dimensional features. Okay. So, with that being said, that's kind of like and quite complicated. But let me just demonstrate one simple examples. Why somehow we can avoid to calculate this phi and explicitly. For example, I'm going to consider the polynomial features of degree of exactly k. Features of degree exactly equal to k. And here we are interested in the situation that d equal to 2 and the k equal to 2. Okay, so then the feature map is basically x1 squared, x2 squared, and square root 2 x1, x2. Then this kernel becomes the following. X and x prime. It is my phi of x and phi of my x prime. So this is a trend. Here I'm doing the inner product here. So this, if we stack them and directly, this is give you something like this. This is should be. So if we consider, this is a row. So this will be a transpose here. So, and we can write it out, explicitly. So this is equal to x1 squared times x1 prime squared plus x2 squared, x2 prime squared plus, and square root 2 times square root 2, it's 2 x1 x2 x1 prime x2 prime. Okay, so if you do that, you are getting x1 prime plus x2 prime square. Okay, then you can rewrite things into a vector. So this becomes I mean, if you write x into a column vector, so this becomes the following: x transpose of x and a square. If we define x is x1 and x2. All right, so and you can see this is quite straightforward. I mean, and all we need to do, I mean, it's basically we calculate the norm, and the square norm of x. Then we take the square out and take the square out of that. That will be calculating the kernels of x and x prime. And you can do this for the general D. Then this feature will be more complicated. So we are getting something like x1 squared to xd squared square root of 2 x1 x2 and a square root of 2 xd minus 1 xd. So this has in the dimension of d times d plus 1 divided by 2. So you can see if we work with the general D, the dimension of feature space is significantly bigger. So this is actually a much bigger numbers. As a result, this K, and you can do the same calculation. This X and X prime, you can do the same math. You find out this is precisely the same. I think I made a mistake here. This should have a prime here. So, yeah, not the norm. Right? So basically, this is inner product between x and x prime. Then you take square, and then you take square out of that. So this is the same thing that if you want to do it right here, this is basically take inner product between x and x prime, then you take square and out of that. So I want to remind you in terms of calculation, number of complexity here. So if you want to do the x and phi x dot phi x prime explicitly, the number of the number of the multiplication that needed is order of d times the d plus 1 divided by 2. So that actually is quite expensive. But if we just simply using this formula right here, this will be an inner product between x and x prime. So this is just order of d. Right, so it's regardless how complicated of this feature spaces that we have, this is significantly smaller than the order of d plus 1 divided by 2. So that means we can get around to using this phi and directly calculate this k, x, and x prime directly. So this gives you some good idea. This whole thing, it's possible. Okay, so in fact, we can even consider something slightly even more complicated. That if we consider the polynomial features of degree up to k. So not only we consider the precisely equal to k, but we also need to consider the degree lower than k. For example, k minus 1, k minus 2, and so on. we still consider the cases that k equal to 2 and d equal to 2. So then the phi x right here becomes 1 square root of x1. So, and we need to consider x to the 0th, x to the 1th, x to the 2th, square root of 2x1, x2. Right? So, I mean, this whole thing, I mean, if we consider that altogether, then this phi x and phi x prime, this is 1 plus 2x1, x1 prime, plus 2x2, x2 prime, plus x1 square, x1 and a square prime, using different color here, plus x2 square, x2 prime square, plus 2 x1, x2, x1 prime, and x2 prime. Okay, so in fact, you can show this is equal to the following thing. This is equal to 1 plus x transpose and x prime square. And you can like simply and expand it out and find out this is actually the truth. So you can actually think about everything. I mean, as follows, like, so, and then let me quickly derive that. So I think that's not a bad idea. So this is 1 plus 2 of, I mean, x transpose and x prime. This is x transpose and x prime square. Then this becomes 1 plus of x transpose x prime square, right? So this is situation for and up to the degree of 2. In fact, I mean, this everything, I mean, works even for general D here. But think about right here, we have 1, 2, 3, 4, 5, 6 in R6. Right? But to calculate everything right here, the only, I mean, expensive part is inner product of x and x transpose and x prime. This is quite cheap to calculate because everything is just 2-dimensional. You only need to and multiply them and twice. So this is, and the cost to do that is significantly cheaper than you write out explicitly for phi x. Then you do this inner product for that, and phi x and phi x prime. So so you can do this, and we can do this with and all sorts of like complexity analysis. So and for example, right here, I mean, in fact, and more and more general, and D, this k x and x prime, it still work. It's still being something like that. So I mean, in order to calculate this whole thing, it costs order of the D. All right, so this is significantly cheaper, but for phi x, to explicitly computing this feature phi x, it will cost about order of d and p, and which is about order of d squared, or d to the k right here. I mean, since we choose k equal to 2, that will be and d squared. That will be, I mean, the amount of time or memories need to be allocated. So, I mean, the comparison, if we just trying to calculate this K matrix right here, which is Kij, and this Ij is from 1 to the n, it will only cost about n squared times of d. Since p is significantly bigger than d, that is totally possible that to calculate the K matrix will be much more efficient than write out the phi x explicitly, because phi x is very hard to write and also takes a lot of memory and time to write explicitly. So that means these features are kind of implicit. We want to make this to be assessed through the kernels. All right, so this is something give you some idea how we actually can calculate this K matrix efficiently, rather than we and write out this phi x and phi x prime explicitly right here. But how this actually will help? Let me just using one simple examples on the ridge regressions. But instead we solve ridge regressions, we are going to use the idea of the kernels. So solve regressions with kernels. So I want to remind you, in the ridge regression, we are trying to solve the following thing. Right? So say we are in, situation that we know this x is in Rn by P, and this situation that P is significantly even bigger than N. So that means my matrix of X is actually a skinny, a fat matrix. So this is fundamentally different from the situation that we had before. So I think I used D here. So let me just using D here. And you can think about this. Columns are actually the features that I already lift up in the high dimensions. So the whole idea is I want to make predictions, write W hat using K, X, and X prime with the kernels, which is my X and X prime transpose. Right. So and the reason that I write X and X transpose this way is because here my X is written in the row vectors. Okay, so if we write out everything to the matrix of K, this is nothing but my X and X transpose. Right, so we know this will be n by n matrix. So I want to write all my solutions with the K matrices. So we consider the situation right here is D is much bigger than N. So that means the number of features are more than the number of the data points. So we have this analytical solution. So my W hat right here is X transpose of X plus lambda of identity of D by D, inverse of X transpose of Y. But we can't use it because here we are using D by D. D is significantly bigger, and also X transpose of X is significantly bigger than N by N. So it won't be ideal to count and to using so matrix size of N by N. And in terms of D by D, it will be much ideal if we could use everything in terms of N by N. So I'm going to show you this is equal to the following. X transpose of XX transpose plus lambda N by N. That inverse times the Y. Okay. So if we can write everything in terms of like that, that would be much ideal because we actually have this X and X transpose. We know X and X transpose is significantly cheaper. And once we add like lambda of identity, it will be cheaper to to take the inverse or like to solve this linear and equations rather than to work on D by D. D by D is significantly larger matrices. So why this is true? Why this is actually correct? So we are going to take a lemma here that is this P inverse. So I think I'm not going to take the same idea right here, but we can look it out right here. So and let's just move out this part of Y because we have the same Y on at the end. So what I'm going to do is I'm going to multiply and we want to show X transpose plus lambda of identity N by N multiply X transpose. Sorry, I think that was wrong. Let me think about this. Oh, sorry, I think they will be like this. By this transpose, X transpose here. So let's calculate this whole thing. This becomes X transpose of X times X transpose plus lambda of X transpose, right? Then what we are going to do is we are going to factor out of X transpose of X plus lambda of identity. In this case, that would be D by D of X transpose. Right, so this is how we get around this. Then what I'm going to do is I'm going to, and we know this right here, they're all invertible. for those part. I'm going to take inverse of this first part first. So this becomes X transpose equal to X transpose of X plus lambda identity d by d of X transpose of X transpose plus lambda identity n by n inverse. Then what we do is we take and take inverse for this part. So this becomes X transpose X plus lambda identity and d by d inverse X transpose equal to X transpose X transpose plus lambda I n by n of inverse. So we prove this factor right here. Right, so this basic says we can move from here to here. So that's good. And basically, we can use this as my training. And we can use similar idea for the prediction as well. So for the prediction, we have y equal to x of w hat. So that means it's a new data of x of my solution will be x transpose x transpose plus lambda identity n by n inverse of y. Okay, so this is the predicted values of y hat. So I mean, in fact, we can make this whole thing much more efficient by vectorize everything. So I mean, in fact, all we know right here, I mean, in order to make prediction is first things, we need to make calculations of this vector times this matrix. And also we need to know this matrix multiplications, which is X transpose right here. So all we need, we define the vector of kx right here is actually a vector of kx x1, kx of x2, kx and xn. So if we do this way, you can get this is being x and x transpose. Well, x of transpose. Yeah, I think it's x transpose. So this is 1 by n. That would be x. And then m by wait. M by d. M by d. And so m by d. Yes. So an x in a and the product of this. Then is in addition, we can write this matrix. This matrix is K 1 1 and the K 1 2 and so on. So at the end, the last one will be K and K1 K of xn, x of n. Right, so this is actually a matrix of n by n. And this can be written out, so explicitly by doing this XX transpose in R in n by n. So that means, in fact, we don't need to get this X matrix explicitly, because this X matrix is n by d. D could be very large. The only thing that actually matters is wait. I think this is, I made mistake. It's transpose here. Yes. So this is, you are getting or it's D, yes, D. This is and D by n, so this is Rn. Right. So what actually matters is this vector of Kx and the matrix of K. And both are and both terms are D independent. Then, and that means we don't actually need a D here. So there will be and significantly faster the situations. All right. So what is the differences here in terms of training and predictions? So the time complexity right here is the kernel trick requires needs order of n squared times d to calculate the k. So I think it's kind of tricky here because I don't want to call this d here. If we call this d right here, it's get confused. In fact, and what we are talking about is actually the p. P is really bigger ones. So I don't want to call the d here. It is truly the p, right? Because we already lift up into high dimensions. P times p, p times p, so we can get around and without using d here, p here. So that will be much more reasonable to work on. All right, so the kernel trick requires n squared times d to calculate the matrix K. And also we need to solve some like matrix vector equations that would take about order of n cubed to solve this K plus identity of n by n times some x equal to y, the w equal to y. So this requires order of n cubed. So the total complexity is n cubed plus n squared times d. And the space complexity, so this is time complexity. And the space complexity is we actually need a space to store this K matrix. This is order of n squared. If we don't using this kernel trick traditional methods, that means actually we need to calculate the phi and explicitly write out the phi. Then we do this least square and the solutions right here. And that means we are actually need to work on this one. The time complexity is order of p cubed plus p squared times of n, because we're trying to solve a linear system size of p by p. And a space one, that will be order of n times p. Both of that is untolerated because it's too expensive. So I can see, and with that we can get around and make everything much and much simpler. And the point right here is everything is independent of D. Okay. All right. So at last we need to make everything more general, right? So and this is we need a more a general framework for everything. So this will be on the second part.